The real science of Star Trek teleportation. Teleportation is one of the most iconic ideas in all of science fiction. You step onto a platform, you shimmer in a beam of light, and in a blink, you're somewhere else. But this is just a plot device for storytellers. The creators of Star Trek, for example, use teleportation as a way of avoiding repeated, expensive shuttle shots when visiting planets. Or could scientists one day invent an actual teleportation device? Does physics really allow teleportation? To find out, we'll need to dig a little into the science. We'll need to look at a little bit of quantum mechanics, a bit of information theory, some energy calculations, and even a bit of philosophy. But first, teleportation is real. We've already done it. Scientists have already teleported. Just maybe not in the way Star Trek shows us. Transporters in science fiction. In the Star Trek universe, transporters are simple, at least in concept. Step 1, scan every atom of your body. Step 2, convert that scan into an energy pattern. Step 3, transmit that energy pattern through space. Step 4, reassemble those atoms at their destination. On screen, it looks instant, safe, routine. Well, except when Scotty or Chief O'Brien has a bad day. However, in reality, each of those steps is monumental. Step 1. Scanning the human body. Let's start with scanning. The human body contains around 7 times 10 to the 27 atoms. That's 1 billion times 1 billion times 1 billion atoms. To teleport someone, you need to know the exact position, the exact angular momentum, the exact quantum spin, and the exact bonding state of every single atom. And that's where the first problem arises. The Heisenberg uncertainty principle tells us that you cannot know both position and momentum with perfect accuracy. And then there's the no cloning theorem. It says you cannot copy an unknown quantum state. In plain English, both of these scientific principles mean you can't take a perfect atomic level snapshot of a human being. Even if you tried, measuring those states would collapse them, which means scanning would destroy the original, i.e. kill the human. A transporter isn't a copy machine, it's a destructive scanner. In scanning you, it would also kill you. Step 2. Converting the scan into an energy pattern. Star Trek describes the scan as being converted into an energy pattern. What might this mean in real physics? In quantum teleportation, you convert the quantum state, not the atoms themselves, into information. That requires measurement, which collapses the state, and a classical channel to send measurement results. But where does an energy pattern come in? The answer is, it probably doesn't. One way to imagine it is that scanning and holding data about each atom's state would require an enormous amount of energy. Storing and transmitting that data is physically expensive. To maintain quantum coherence, i.e. keeping the state intact, we may need ultra-cold temperatures, precise, stable fields, and error correction. The energy pattern in Star Trek implies converting matter into energy. However, actually converting mass to pure energy is, whilst theoretically possible, practically it's catastrophic. You'd need an almost infinite energy, and you'd be destroying all the matter. In science now, we don't convert scanning into energy, we convert it into information which is carried via entanglement or via classical channels. Step 3. Data transmission. Okay, let's imagine we somehow manage to scan a human being anyway. Now we need to send that information. How much data are we talking about? At a minimum, about 10 to the 28 kilobytes. That's billions of times more than all the data humanity has ever created up to this point. If we tried to send the data for a single human being on today's networks, it would take longer than the age of the universe. Maybe compression. Could we zip a human being? Maybe. Most of biology is redundant. DNA only has 4 bases, for example, so we don't need to store what we can assume. Many proteins have repeat structures, and we can make assumptions here to aid compression as well. But even with extreme compression, the data requirements are still astronomical. There is a glimmer of hope. Quantum teleportation. I mentioned earlier that scientists have already teleported. This is real. We have already teleported single particles. Quantum teleportation uses entangled particles to transmit the state of one particle to another across space. In 1997, Innsbruck University teleported the state of a photon approximately 1 meter. In 2004, researchers at NIST teleported 100 billion atoms of cesium about 35 centimeters, although this was technically the teleportation of an entangled ensemble rather than individual atoms. In 2017, Chinese scientists teleported a photon state to a satellite in orbit 1,200 kilometers away. In 2019, Fermilab and Caltech teleported qubits over 44 kilometers of optical fiber with a 90% fidelity. This means that only 10% was different to the original. Remember the Heisenberg uncertainty principle and no cloning theorem from earlier. Sounds incredible, but remember, this is only the teleportation of information, not matter, and the current teleportation process still needs a classical channel, which means it's limited by the speed of light. So, no instant starship transport. At least not with today's physics, not with our current understanding of the universe. Step 4. Reassembly. Suppose we somehow manage to scan and transmit. Now we must reassemble the human at the destination. To reassemble a person, we need some sort of molecular assembler, a 3D printer for atoms if you like. But we don't have nanomachines that can reliably build proteins yet, let alone an entire human. Reconstructing 37 trillion living cells is far beyond our current reach. And the energy cost. Einstein's E equals mc squared tells us the numbers. For a 70 kilogram person, the energy is 70 times 3 times 10 to the 8 squared, or 6 times 10 to the 18 joules. That's about the total energy consumption of the entire world in a year for one human transport. And error tolerance is brutal. One single misplaced atom in DNA could trigger cancer. One single wrong connection in your brain, and you may not be you anymore. To rebuild perfectly, the error rate must be 0, and no system we currently know comes even close to that. Energy costs and information theory. Information isn't free. According to Landau's principle, erasing one bit of information requires E equals kT ln2, or 3 times 10 to the minus 21 joules at room temperature. For a human body, that's 8 times 10 to the 28 kilobytes, or the energy requirement of 2 times 10 to the 8 joules. That's equivalent to detonating 25 kilos of TNT just to delete the data. That's not even counting the reassembly cost. A roadmap to Star Trek. So, what might a roadmap to Star Trek teleportation look like? How might we be able to get there? Step 1, we would need some sort of perfect quantum network, a high-fidelity teleportation of photons and ions. The quantum internet is already being tested, so we're kind of on the way with step 1. Step 2, we would need to be able to teleport complex molecules. We'd need to be able to teleport proteins, DNA strands, perhaps even small viruses. Step 3, once we've done that, we would need some sort of ultra-fast atomic scanning. Today's scanning tunneling microscopes can image atoms, but only one at a time. At that speed, scanning a human would take over 30,000 years. Step 4, if we get the scanning sorted, then matter assembly at atomic resolution is next. Imagine 3D printers that place atoms instead of plastic. This is the holy grail of nanotech, but is a long way off. Step 5, integration. We would need to be able to combine these new scanners, new quantum networks, and new assemblers into one seamless process. Unfortunately, each of these steps is not just one breakthrough, it's dozens, maybe even hundreds, each of their own worthy of a Nobel Prize. Recent advances. There are real promising recent advances. Quantum repeaters are being developed. in the QRAM lab in Switzerland using rare earth-doped crystals. These extend teleportation distances beyond single links. Quantum memories are being developed in Australia's ANU Quantum Memory Lab using cold atom ensembles to store photon states. These could store states briefly for error correction. Quantum internet projects are underway in the US, China and Europe, and IBM has already arranged individual atoms to spell the word IBM. Proof of concept for atom-by-atom placement is possible. Each advance chips away slightly at that transporter dream. Challenges. Despite these recent advances, the obstacles are still enormous. The uncertainty principle. Remember, you can't know both an atom's position and its momentum. This would somehow need to be overcome or bypassed in order to have a working teleporter. The error tolerance. Even if you manage to get a human teleportation 99.9999% right, that's still 10 to the 21 mistakes. And remember, it only takes one mistake to trigger cancer, or for the new you to have a totally different personality. Up till now, we've ignored the identity paradox. If you were teleported, i.e. you were scanned, destroyed and rebuilt, is that still you, or just a perfect copy of you? In Star Trek, they have a component called the Heisenberg compensator in their teleporters. This somehow magically solves a lot of these problems. We unfortunately have no such luxury. Numbers. Let's run some number comparisons. If scanning one atom takes 1 nanosecond, then scanning a human would take 30,000 years. To store human atom data would require a data center the size of a city. Energy. To convert a 70-kilogram human into energy would require 6 times 10 to the 18 joules of energy. This is equivalent to a few thousand nuclear bombs worth of energy. Even ignoring the identity paradox, the physics itself looks unforgiving. What about some speculative workarounds? How might we get around some of these? Could there be shortcuts in the future, like the Star Trek Heisenberg compensator box? One potential is just to teleport some parts. A mind upload, for example. Instead of every atom, maybe only transmit the brain, and maybe some DNA as well. Rebuild the rest locally. Maybe some nanobot relays. Instead of beaming particles, swarms of nanobots disassemble you and rebuild you at the destination, each nanobot remembering the part it disassembled. Maybe wormholes. This wouldn't strictly be teleportation in the Star Trek sense, but a way around space-time altogether. Partial teleportation, maybe start with things other than whole humans. Molecules, medicines, or organs, for example. Philosophy of identity. So what about the philosophical part of teleportation? Let's imagine we find a workaround to the physics problems and we get teleportation to work. What about identity? Imagine the perfect original you is destroyed. A perfect copy appears elsewhere. That copy thinks it's you, feels like you, remembers your life. But is your consciousness continuous, or did the original you just end? This is one that is known as the Teletransportation paradox. Star Trek effectively ignores this. Characters beam down, beam back, and carry on. But in reality, the transporter might not be a transporter, but the most efficient killing machine ever invented. So, can Star Trek's transporter exist? With today's science, no. Scanning is impossible, transmission is impractical, and reassembly is currently unthinkable. But teleportation itself, yes. Quantum teleportation, moving information, not matter, is not science fiction, it's today's science fact. It won't beam Captain Kirk to a planet, but it could revolutionize communication. The quantum internet is already being developed. Unhackable cryptography is part of this. New ways of connecting people across the globe is also part of it. Science fiction shows us what might be possible, but it also forces us to confront the limits of science, and sometimes the limits of identity itself. For now, we'll just have to walk.